How is the glomerular filtration rate, or GFR, generated and regulated? And what effect does this have on stable kidney function and blood pressure?
Glomerular filtration rate, or GFR, is the volume of filtrate formed by both kidneys each minute. In a healthy adult, it averages about 120 to 125 milliliters per minute, which adds up to about 180 liters of filtrate per day. But only about 1 to 2 liters actually leaves the body as urine, meaning most of what is filtered is reabsorbed. GFR is one of the most important measures of kidney function because if filtration is too low, wastes build up in the body. If it's too high, the kidneys can't reabsorb needed substances quickly enough, so the body tightly regulates it. Filtration happens at the glomerulus and is controlled by Starling forces. Remember, Starling forces are the pressures that control the movement of fluid in and out of capillaries. They're the balance between hydrostatic pressure, which is pushing fluid out of the blood, and oncotic pressure from plasma proteins, which pulls fluid back into the blood. Together, these forces determine whether fluid leaves the capillaries to enter tissues or is reabsorbed back into the bloodstream. So filtration at the glomerulus is controlled by these forces just like any other capillaries, but under much higher pressure. Here, there are three main pressures at work. Glomerular hydrostatic pressure is the blood pressure inside the glomerular capillaries, pushing water and solutes out of the blood and into Bowman's capsule. This is the main driving force and is normally around 55 millimeters of mercury. Opposing this are two forces. Capsular hydrostatic pressure, which is the pressure of fluid already in Bowman's capsule pushing back against filtration, and blood colloid osmotic pressure, which is created by plasma proteins pulling water back into the blood. When you subtract the opposing pressures from the glomerular pressure, you get net filtration pressure, which is usually around 10 millimeters of mercury. Even though this seems small, it's enough to produce large amounts of filtrate. The kidneys can regulate GFR independently of systemic blood pressure through a process called autoregulation. This happens in two major ways. The first is the myogenic mechanism. If blood pressure rises, the afferent arteriole stretches. In response, its smooth muscle contracts, narrowing the vessel and reducing blood flow into the glomerulus, protecting it from damage and keeping GFR stable. If blood pressure falls, the afferent arteriole dilates, allowing more blood in and helping maintain filtration. The second mechanism is called tubuloglomerular feedback, and it involves the juxtaglomerular apparatus, an area where the distal convoluted tubule touches the afferent and efferent arterioles. Specialized cells here, called the macula densa, monitor the concentration of sodium and chloride in the filtrate. If GFR is too high, filtrate moves too quickly and there isn't enough time to reabsorb sodium. The macula densa senses the increased sodium chloride and signals the afferent arteriole to constrict. This decreases blood flow into the glomerulus and reduces GFR back to normal. If GFR is too low, the macula densa causes dilation of the afferent arteriole and stimulates nearby juxtaglomerular cells to release renin. Renin begins the renin-angiotensin-aldosterone system, or RAS. Renin converts angiotensinogen from the liver into angiotensin 1, which is later converted into angiotensin 2 by ACE in the lungs. Angiotensin 2 constricts blood vessels, especially in the efferent arteriole, increasing pressure in the glomerulus and raising GFR. It also stimulates aldosterone release from the adrenal cortex, increasing sodium and water reabsorption, which increases blood volume and blood pressure. Finally, during times of stress or blood loss, the sympathetic nervous system activates. Strong sympathetic stimulation can constrict afferent arterioles, greatly reducing GFR to conserve water and redirect blood to vital organs like the brain and heart. Moderate stimulation, however, primarily triggers renin release and RAS activation rather than shutting down filtration completely. Altogether, GFR regulation is a balance between local kidney control and systemic control. The kidneys use autoregulation to keep filtration steady from moment to moment, while hormones of the nervous system step in during larger changes in blood pressure, blood loss, dehydration, or stress.